Section 1.6, predicates and quantifiers. So in a previous textbook, the predicate was referred to as a propositional function, so you might see that as well. Same thing. So a predicate or a propositional function is a logical statement whose truth value is a function of one or more variables, and it's called a predicate. So that's going to look something like P of X. And then, of course, we need to know what kinds of values are in X, and that's going to be the domain, just like it is in algebra. So the domain of a variable and a predicate is the set of all possible values for the variable. And like in algebra, this could be real numbers, integers, and so on. Now, with these predicates, we also have the concept of quantifiers. The universal quantifier is a for all statement, and we use an upside down A for that, and we write it as follows. And the way that we read it is we say for all X, P of X, and that P of X is said the same way that we use for regular old functions. The existential quantifier is a backwards E and is read, there exists an X such that P of X. There exists an X such that P of X. I'm not going to spend too much time giving examples of these because there are some really great examples in your zyBooks. So I just kind of want to give you the basics. A universal quantifier or a universal quantified statement is true. Well, let's go ahead and fill this in first. When are each of these true and when are they false? So a universal quantified statement is true if that P of X statement is true for every single X in the domain. So I'll put in the domain in parentheses because it's usually understood, but that does actually need to be in there. So if we say that our domain is integers and a certain statement is only true for a non-integer real number or a rational number, then this universal statement would not be true. And it would be false if there is even one value of X in the domain for which P of X is false. So it's false if there is one, or at least one, but it only takes one X in the domain, of course, in the domain for which P of X is false. As for the existential quantifier, this is going to be true as long as there is one X that makes it true. So it's kind of like this. These two are justified in a similar way. So if there is at least one, all it takes is one X in the domain for which P of X is true. And think about the existential quantifier. What would make that false? Okay, so if I say there exists an X such that P of X, that's only going to be false if there is no X for which it is true. In other words, P of X is false for every single value of X. So it's false if P of X is false for every, I can read that a little bit nicer. I'll try again. This is false if P of X is false for every X in the domain. You might notice again that this is a very similar argument to justifying why a universal statement is true. And then finally, a counterexample for a universally quantified statement, again, that means a for all statement, is an element for which the predicate is false. And this is a pretty useful tool when we are writing certain kinds of mathematical proofs. And this concludes section 1.6.